To visualize human physiology in real time, physicians require highly unstable atoms. This animation shows a glowing atomic nucleus, illustrating that extreme physical instability. Because of this extreme instability, these atoms undergo rapid exponential decay. Often they vanish into stable, useless elements in a matter of hours or even minutes. Unlike traditional pharmaceuticals, you cannot stockpile radioisotopes. There are no shelves of inventory. This creates a strict geographic constraint. Clinical isotopes must be manufactured either in a continuous, rolling production cycle or directly at the point of care. This diagram illustrates the three distinct architectural engines of production engineered to solve this bottleneck: cyclotrons, nuclear reactors, and radionuclide generators. To master clinical molecular imaging, you have to trace every single radiopharmaceutical back to its specific method of physical manufacture. Look at this photograph of a heavy, industrial-scale, vintage cyclotron machine. It operates on a principle called nuclear bombardment. This top-down vector schematic illustrates the internal anatomy of a cyclotron vacuum chamber. The process begins when particles are injected directly into the center. The structure consists of two hollow D-shaped electrodes. These are known as the Ds. A high-frequency alternating voltage is applied across the gap between the two Ds. This alternating voltage flips the electrical charge, violently accelerating the injected particle back and forth across that central gap. At the same time, a massive static magnetic field is applied perpendicular to the plane of the Ds. This magnetic field forces the accelerating particle outward. Instead of a straight line, its back-and-forth path converts into a continuously widening spiral. Eventually, the accelerating particle reaches the outer edge of the Ds and shoots tangentially into a peripheral bombardment chamber. Inside this chamber, the high-speed particle strikes a highly specific target material. The impact forces a change in the atomic structure, forging the desired radioisotope. For example, by bombarding oxygen-18-rich water with protons, we produce the proton-rich isotope fluorine-18. This image shows a patient positioned for a scan. Fluorine-18, the critical isotope used in FDG PET scans, has a half-life of only 1.87 hours. Cyclotrons are also used to produce other clinically vital isotopes, including gallium-67 and thallium-201. By relying purely on electromagnetic forces, cyclotrons manufacture specialized proton-rich isotopes. Because they are proton-rich, these atoms generally decay via positron emission. This photograph looks down into the blue-tinted water of a nuclear reactor core, where the physics shift entirely from particle bombardment to neutron activation. This diagram models a single uranium-235 atom. The engine of the reactor relies on U-235 undergoing spontaneous fission, splitting into fragments and ejecting 2 to 3 free neutrons. These free neutrons strike adjacent uranium-235 atoms. This creates a highly unstable uranium-236 intermediate, which immediately splits, releasing more neutrons and driving a self-sustaining chain reaction. To harness this massive energy release, engineers rely on two structural constraints. The first are the moderator rods. The fast fission neutrons released by splitting uranium possess too much kinetic energy. The exact function of the moderator rod is to physically slow these highly energetic, fast-moving neutrons down. This is necessary because slower neutrons have a vastly higher probability of interacting with other U-235 nuclei. Slower neutrons are simply more efficient at initiating additional fission events. The second constraint relies on control rods, typically constructed of cadmium or boron. Unlike the moderator rods, control rods act as the reactor's brakes. They completely absorb neutrons without undergoing fission themselves, halting the spread of the reaction. To harvest medical isotopes within this environment, specific non-radioactive target materials are lowered into open ports directly in the active core. These target materials are bombarded by the slowed neutrons. The atoms capture a neutron, gaining mass and converting into a heavy radioactive isotope. This process of neutron capture produces heavily tested clinical outputs like iodine-131, xenon-133, and molybdenum-99. Because neutron activation creates isotopes with an excess of neutrons, they sit above the line of stability. Consequently, these reactor-bred isotopes tend to decay via beta emission. Controlled fission allows reactors to mass-produce heavy, neutron-rich parent isotopes, providing the raw material for the rest of the clinical supply chain. Even with reactors running constantly, a critical logistics gap remains. Certain vital isotopes have half-lives measured in seconds or hours, making physical transport from a reactor to a hospital impossible. The solution is the radionuclide generator. This photograph shows a heavy, lead-lined canister next to its sterile collection vial, manufacturing short-lived isotopes at the bedside. This cross-section diagram reveals the internal anatomy. A sterile glass column encased inside that heavy lead or depleted uranium shielding. Inside the column is a chemical setup. A slow-decaying parent radionuclide is firmly adsorbed onto the surface of an aluminum matrix. Over time, the parent isotope naturally decays, transforming directly into the required, shorter-lived daughter radionuclide. To extract this fresh isotope in a process known as elution, a solvent, typically sterile saline, is passed through the top of the glass column. This system relies on chemical selectivity. The saline is engineered to detach only the new daughter radionuclide, leaving the parent isotope firmly locked to the alumina. The daughter-rich saline is drawn downward by a vacuum action and pools into a collection vial at the base, ready for immediate use. Immediately after elution, the concentration of the daughter isotope drops to 0, but as the parent continues to decay over the next day, the daughter isotope steadily builds back up for the next extraction cycle. This is exactly how clinics acquire krypton-81M from a rubidium-81 parent, and more importantly, how they harvest technetium-99M from a molybdenum-99 parent. These generators serve as miniature, point-of-care chemical refineries, completely bypassing the geographic limits imposed by rapid radioactive decay. The entire discipline follows a strict logic. The clinical indication dictates the required isotope, and that isotope's atomic structure dictates the machine required to build it. This flowchart traces the supply chain backwards. Molybdenum-98 undergoes neutron activation in a nuclear reactor, forging the parent isotope, molybdenum-99. This MO-99 is loaded into shielded generators and shipped to hospitals. Finally, clinicians elute the generators, harvesting the short-lived technetium-99M directly into a vial. This specific, codependent supply chain is critical. Technetium-99M is utilized in 80% of all nuclear medicine studies worldwide. While reactors and generators operate in this tightly linked loop, cyclotrons operate as independent sites, synthesizing proton-rich PET isotopes like fluorine-18 entirely on their own. Ultimately, every image you evaluate on a PACS monitor is the direct downstream result of applied particle physics, controlled nuclear fission, or targeted chemical elution.